Hi, this is Mrs. Hedden. I'm going to work out answers to power problems 71, 75, and 76. Let's start with 71. An engine moves a boat through the water at a constant speed of 15 meters per second. The engine must exert a force of 6 kilonewtons to balance the force that the water exerts against the hull. What power does the engine develop? So we're hunting for power. And we have a velocity here, and we have a force. So let's take a look at what we need for power. The equation for power is work divided by time. And of course we know the equation for work is force times distance divided by time. We have the force. Force is equal to 6 kilonewtons. We might as well go ahead and convert that to straight newtons. K stands for 10 to the third, so that's 6 times 10 to the third newtons. And then we have this velocity of 15 meters per second. What is this meters per second? Well, let's look at the power equation. The power equation has a distance divided by a time. Velocity has a distance divided by a time. So the 15 meters per second can take the place of distance over time in the work equation. So now, once you make that realization, it becomes easy. We have 6 times 10 to the third newtons for our force, and we have 15 meters over 1 second for our distance in time. And then we just do our conversions and our multiplications, and we have 9 times 10 to the fourth watts. And so ends 71. 75 looks more interesting. We have oil pump. In 35 seconds, a pump delivers 0.550 cubic meters of oil into barrels on a platform 25 meters above the intake pipe. The oil's density is 0.820 grams per cubic centimeter. A, calculate the work done. B, calculate the power produced. So we're hunting for work. Work equals force times distance, if everything is parallel. In this case, if we're taking the oil up, the only force that's parallel to that would be the force of gravity. So we're interested in the force of gravity in order to calculate this work. We have a distance. The distance is 25 meters. We have a time, which will come handy for the power, and we have these other two odd pieces of information. So let's write all this stuff down. Our distance is equal to 25 meters. Our time is 35 seconds. We have a volume equal to 0.55 cubic meters. And we have a density equal to 0.820 grams per cubic centimeter. Wanting for work. Well, force of gravity, if that's the force that we're going to use, we know is equal to m little g. So if we could find the mass of the oil being risen up in the intake pipe, then we could find the force of gravity, and we'd be in good shape. So we need to find the mass. Well, we have a volume here. The volume is in cubic meters, and we have this density in grams per cubic centimeter. So it seems like we could get grams and get a mass out of all of this. So let's try some dimensional analysis. To do this, we've got to get the centimeters in cubic meters, because this is in cubic meters. So we've got to convert. So that's a fun thing. We've got 0.82 grams. So to convert, we're going centimeters to meters. There's 101. And that'll get rid of one of the centimeters, but we've got two more that we have to handle. So 100 centimeters per 1 meter. Another 100 centimeters per 1 meter. This centimeter crosses this. This cancels out with this. And we would have 8.2 times 10 to the fifth grams over meters times meters, but that's cubic meters. So we're in good shape, or we're getting there at least. So we have 8.2 times 10 to the 5th grams over cubic meters. But our mass has to be in kilograms, so we've got to convert the grams to kilograms. So there's 1,000 grams in 1 kilogram. The grams will cancel out. And that gives us 8.2 times 10 to the 2nd kilograms per cubic meter. So it's looking better. So every time the intake pipe pulls up a cubic meter of oil, it's carrying 820 kilograms. Well, how many cubic meters does it take up? Going back to the original problem, it says it lifts this many cubic meters every 35 seconds. So how much does that many cubic meters of oil weigh? What is its mass? We've got 0.55 cubic meters times, I'm going to just make it 820 kilograms for every cubic meter. Cubic meters cancel out, and that gives us 451 kilograms. At last, we've got a mass. Now we can find the force of gravity. Force of gravity is mass times little g. So it'd be equal to 451 times 9.8. So the force of gravity that the pump is lifting is equal to 4,419.8 newtons. So we have a force. Going back up to our original listing of stuff, we have a distance. So we can use this equation because everything is parallel. Work is equal to the force of gravity times the distance in the vertical direction. So it's equal to 4,419.8 newtons times 25 meters. So it's equal to 110,495 joules. First part's answered. Now we want to find out the power. Power is equal to work divided by time. Well, we already know what the time is from way back up there. The time was 35 seconds. So we can plug that back in. So we get 3,157 watts as our power. And we finished 75. Let us move on to 76. Okay, in 76 we have a 12-meter long conveyor belt inclined at 30 degrees. It's used to transport bundles of newspapers from the mailroom up to the cargo bay to be loaded onto delivery trucks. Each newspaper has a mass of 1 kilogram, and there are 25 newspapers per bundle. Determine the power that the conveyor develops if it delivers 15 bundles per minute. So I'm going to do a quick drawing here. We've got this incline, and we've got these bundles of newspapers being hauled up. And we know the incline has an angle of 30 degrees. And we know that the distance of the ramp is 12 meters. We're hunting for power. What else do we know? One newspaper equals 1 kilogram for mass. Mass of one newspaper equals 1 kilogram. We know there's 25 newspapers, and we know that we have 15 bundles per minute. The formula for power is equal to work divided by time. And work, of course, is force times distance times cosine theta divided by time. We have a theta here, but is that the same theta as this? Remember that this theta in the work equation has to be equal to the angle between the force being exerted and the distance traveled. Well, what force are you overcoming when you lift newspapers up a conveyor belt? The force of gravity. So the force of gravity goes straight down. Does this 30-degree angle have any difference between the direction it's moving and the force of gravity? No. So this is not the same angle. This does not equal theta in the cosine theta part of this equation. Not equivalent. But if we're going against gravity, then we want to find some vertical distance. Vertical distance. Like the lab, like the notes from Monday, we want to find this vertical distance dy. If we have that, then we've got a force that is vertical, and we have a distance that is vertical, and we can find the work. And then we've just got to figure out time. But we've got minutes in here, so somehow we're going to be able to get time out of all this. Okay, so let's do the easy thing first. Let's find dy. This is the opposite side of this particular angle. So SOHCAHTOA, we're going to use the sine. And we've got the hypotenuse. So we know that 12 meters times the sine of 30 degrees is going to equal that dy. Doing some quick calculations, that's equal to 6 meters. So we now know that's 6 meters. So we've got our distance. Now we just have to figure out what this force of gravity is. Well, in the previous problem, in order to figure out the force of gravity, we had to find the mass. So it seems like that would make sense, again, that if we can find the mass of the bundle, then we can take the mass times little g and find the force of gravity. So we'd be in good shape. Now we've got to figure out how to find the mass of a bundle. Well, I've got the mass of one newspaper. So this really just becomes a gigantic dimensional analysis problem. So mass, and we have 25 newspapers in one bundle. So if we have 25 1-kilogram objects in a bundle, it makes sense that the mass of a bundle is equal to 25 kilograms. Okay, we've got the mass of a bundle. Let's move on. We have 15 bundles. We've got the mass of the bundle, so now we can find the force of gravity of a bundle. That'd be equal to the mass times little g, which would be 25 times 9.8. So the weight of a bundle is equal to 245 newtons. So now we can figure out the work done. The work done is just work equals force times the distance, and we're just worried about the y ones here. So that'd be 245 times 6 meters, and that gives us 1470 joules. But for power, we need to have it a time in there. Well, there's a lot of ways to approach this problem, but going back to the original stuff, we know we have 15 bundles delivered every minute. So how long does it take to get one bundle up? Well, let's try this. See, if 15 bundles in 1 minute, 1 minute is 60 seconds, that's 60 seconds, because our time's going to have to be in seconds, then that's equal to 0.25 bundles per second. Or, multiplied by 4, we get 1 bundle every 4 seconds. So we know what the work is per bundle. So our power would be equal to the work done divided by the time. So per bundle, our work done is 1,470 joules divided by 4 seconds, which gives us 367.5 watts. Now there's lots of ways to approach this problem. That's probably the longest route. Another quicker way is, again, what I alluded to of just using dimensional analysis. I want to do that real quick. So looking at my setup, I have 15 bundles delivered every minute. I have 25 newspapers in a bundle. Okay. Each newspaper has a mass of 1 kilogram. And let's see, 1 minute is 60 seconds. If I start crossing things out, the bundles are eliminated, the newspapers are eliminated, the minutes are eliminated, and I have kilograms per second. Multiplying this all out, I get 6.25 kilograms per second. Kilograms I can change into a force. That would be 6.25 times 9.8 divided by 1 second. I get 61.25 newtons per second. But I have to add in that distance. I have to multiply the distance because work is force times distance. So I've got the force and I've got the time. So I need to add the distance. So my power is equal to my force, 61.25 newtons, times my distance, which is 6 meters, divided by that 1 second. And I get the same answer I had before. Power is equal to 367.5 watts. This is just a cleaner way of doing it, I think. Whichever way works for you, though. Thank you very much for your time.